This section covers solver-specific details, how to get solver data in and out of HyperMesh, and in particular HyperMesh's ply-based modeling architecture and zone-based modeling. We talked briefly about zone-based modeling in the introductory set of videos, but I want to show this slide again. And I show it because most solvers operate using zone-based properties. What I mean by a zone-based property is that each area or location of created these manually. We define each of these unique stacking sequences and manually assign each of these properties to the appropriate elements, which represent the area that zone covers. The major challenge with doing these types of models by hand usually is that if there are any ply drops, we have a lot of duplicate data floating around. For example, we can see that ply 7 traverses through all 3 of these zones in this example, and so it has to be defined 3 times. There are valid use cases for zone-based modeling though, but in general, if you don't have a specific reason to, I suggest doing the ply-based modeling workflow we talked about previously. In this section, we will cover a hand-built from scratch zone-based model, but most of our focus will be on the typical use case for interacting with solver data. Generally, there are 2 starting points. The first is if you're maintaining your solver deck as a HyperMesh database. You'll be starting here. Anytime you need to get that data out to a solver, you can do what's called a laminate realization to convert the ply-based data to zone properties, and you can finish with a solver deck export. If you're working with existing solver deck data, which has composite zone-based properties, you can import that into HyperMesh, do what's called an absorb on the zone-based properties, which converts them to a ply-based model, and then you're back to where we started here with the HyperMesh composite model. For example, if we're working in OptiStruct, on the left we have a ply-based model definition. We can see, and this is the same example as that zone-based slide, we have 7 plies, some list of orientation, some thickness, and their stacking sequence. If we realize this data, it gets converted to zone-based solver properties, which in the case of OptiStruct or Nastran is a pCompG. And this set of text represents exactly the same model in zone-based modeling as this ply-based side over here. If we wanted to get this zone-based data back to a ply-based model, we can absorb the properties back into that ply-based model. And with that, we'll go ahead and get into tutorials on manual creation of zone-based properties, on how to import them into HyperMesh, and how to do these conversions between ply-based and zone-based models. And then we'll finish out on solver-specific details that you have to pay attention to if you're working with a ply-based model or a zone-based model. This video covers manual zone-based property creation. In general, and if you're not sure, I suggest using a ply-based modeling method, but there are certain use cases where a zone-based model can come in handy. For this example, we'll build a full hat model just like we did in the ply-based version, but we'll be using zone-based cards directly this time. We're going to be working in OptiStruct, but the workflow and the property cards look very similar in the other solvers. We'll start with a file open, and I'll go ahead and grab this hat zone creation model. It's the same database that we started with for the introductory ply-based set of videos. And so I'll start by setting my orientations, my stacking direction, and my material reference. I'll do that in the model composites composite browser. With a right-click orient, I'll do element normals. I am moving a little bit faster this time since we covered this in the introductory set. Those look correct. For my material reference, I will grab all the elements again, and I'll use a system method on this local system. At this point, the rest of my work will be back in the model browser. We don't do this in the composite browser because it is focused on engineering-based data, so ply-based data and not zone-based solver specifics. We'll close out, and back in the model browser, I can create properties under model and properties here. I'll go ahead and select the appropriate type, which for OptiStruct is a PCompG. And I'll also, while I'm in here, set my Z0 to 0, such that we're stacking from the elements, and the elements represent the tooling geometry. I'll leave the rest default for now. If I come into my Properties tab, we can see this PCompG folder here. I can either double click on it to access just a list of all the properties that have this card image, or alternatively, and usually what I prefer under Preferences and Browsers, is to just show the entities directly in the model browser. I'm going to define 2 zones so that this model is analogous to our ply-based version. The first takes the full 8 plies on the left side of the screen right here. The right has a ply drop of 2 of the plies and is just the plies on the right side of the screen. To define layers, I can come down to my PCompG here and input a number of layers. So I'll start with 8. And before I actually create those, I will just duplicate this property as well for the right-hand side property. So moving on with zone 1, I have these 8 layers defined. I can come into the table editor here. I'll provide a global ply ID for each. We'll talk about the importance of the global ply IDs later, but in general, I suggest setting them. These are analogous to something like a ply name or ply ID, and tell HyperMesh how a ply transverses through zones. For materials, I'm just left-click and holding here. I'll select a material. Maybe we'll do glass for all of them, just because it's convenient, and I will reset the middle 4 to my carbon material. Similar for thicknesses, just left-clicking and holding here. Specify a thickness for each material. And then I'm going to come in and set my orientations here. That all looks correct. And like I said, we're in OptiStruct, but this will be very similar in any of the other solvers. So that's my first zone. I'll go ahead and assign it here. I'll just change the colors on these so I can see the difference. And with a right-click, assign, I will go to elements, and I'll just use a convenient selection method. So that assigns that first zone with the 8 layers. If I turn on thickness, I can see that I do have the property defined and I get a thickness here. So we'll do the same thing on the second zone. We have 6 layers going through this zone. And I'll specify how my layers connect. And just like last time, I'll grab my materials. These two plies at the center of the stack take a carbon. My thicknesses. And my orientations. And I'll finish this out by assigning this property to the appropriate location. And with that, this model is now at least mathematically equivalent to the ply-based version we built in the introductory tutorial. In the previous video, we defined the table data on the zone-based properties manually. It is also possible to import this through an Excel spreadsheet. We'll go ahead and open the same model that we used for the zone creation. And at this point, I do the same steps that I did previously, setting my orientations. We'll go ahead and omit those, though, for brevity. And to import table data onto my properties, I can start by creating one. I'll go ahead and select a PCOMG again. Set the same offset as previously. Close. We have two of them, so I'll just duplicate this once. And while I'm in here, I will assign it to my elements. Same thing for zone 2. And now to actually populate the table data in each of these zones, I can select one of them, come down to our table entry here, and with a right click on, in this case, number of plies, I can import from file. If you're not sure of the schema, you can just go ahead and define a simple zone-based property in whatever solver you're using and export to file first. In the case of OptiStruct, it looks like this. So I'll go ahead and import. I do, before I run that import, have to close my Excel app. And now I can right-click import and bring that data in. Same step for the second zone. And just to recap again, that shows an alternative method to bring the table data in if you're building a zone-based model. This video covers zone-based property conversion to ply-based models through a process called property absorption. I'll start with a file import solver deck. I suggest using whatever solver you're going to be building these models with or using. For the purposes of this demo, I'll use OptiStruct. And OptiStruct does support ply-based data directly, but for the purposes of this demo, I'll use this zone-based version of the composite data. We'll go ahead and import. This is a fully defined composite model using zone solver cards. So we have those two PCOMGs, which we actually created by hand in the previous video. And to convert this data into a ply-based format, I can come to the Model Composites browser, and to access the Absorb tool, it's a right-click, Absorb, Zone Properties. I'll go ahead and select any properties that make up my laminate. Usually the default options are all right here. I'll go ahead and run. And upon running this tool, we'll see that my zone-based data is deleted and replaced with a template property, which takes on all the unique solver attributes of the previously defined zone-based cards. If you have more than one combination, for example, multiple Z-knots, you'll get multiple template properties assigned to the appropriate elements. And then I get a laminate with the 8 plies we've been interacting with, along with ply shapes. If I do a quick review of these, we can see that they're all properly defined. One important point when you're doing these conversions from zone-based to ply-based is the importance of global IDs or names. Depending on the solver, different entries are used. In the case of OptiStruct, it's a global ply ID. Same thing for Nastran. For Abacus, it's a string with the name of the ply. And what these do is specify on the zone-based cards how a ply transverses through these zone-based property cards. So for example, just a very simple model here. We have 2 zones. The zone on the left has 3 layers. The zone on the right has 1 layer. And there are actually 3 ways these zones could connect. All these are mathematically equivalent, but for the purposes of manufacturing having accurate ply shapes, there are differences. Specifically, in this example, ply 1 could connect all the way across zone 1 and zone 2, or ply 3 could. Both share the same orientation. There's a third possibility, which is there's no ply crossing the zone boundary. It's 3 unique plies on zone 1 and a separate unique ply on zone 2, which is maybe butt spliced against ply 2. And so if our zone-based solver properties do define a global ply ID or a global ply name or so forth, that explicitly tells the absorption algorithm how to connect these plies. So for example, if we used a global ply ID of 1 on this first layer of zone 1 and zone 2, the absorption algorithm will connect those 2 layers together in the form of a single ply shape, which crosses those boundaries. And we can see that in this model here, where we had those 2 zones previously defined, and we get several plies that are connected across the zone, determined by that global ID. In most solvers, it's not a requirement, however, that you actually have a global ID, and some solvers don't support that attribute at all. In which case, the absorption algorithm will still run. It just has to make a guess of which of these possibilities is correct. And when it's doing that, it's just starting from the outside of the stack, going across zones, looking for plies with the same orientation and thickness and material. If it finds those, it pairs them together. If it doesn't, it creates a new ply. So again, if you're working with a solver that does have these global IDs, they are important, and this is why it explicitly defines how a ply transverses from zone to zone. And with that, this zone-based property data is converted to an equivalent ply-based model, and now we can have and perform all the same functionality that we've been demoing previously with the ply-based modeling data. So orientations all work. If I go to my one direction, for example, we can look at a couple of plies. You see that orientations are correct. I can look at my through thickness views. Zone-based data does support detailed thickness, but layers are not supported. You would have to absorb this data like we just did into a ply-based model, and then you can view each of the ply layers as well. So again, upon absorption, a fully defined ply-based model. This video covers ply-based to zone-based model conversion, which allows us to convert our generic ply-based data into solver-specific zone cards that we can export as a deck to a solver. So to start, we'll do a file open, and we'll grab a model this time. Typically, this is going to be some sort of model that you're maintaining all your composite data in, and you just need to export it for a solve. I'm demoing in OptiStruct with this plybase.hm. If you're working with another solver, the equivalent HM for each solver is provided. So here's this same ply-based model we've been working with. I have the 8 plies stacked in a laminate, a couple shapes. I have my template property. And now I want to get this data out to a solver. Again, OptiStruct understands this data directly, but any other solver other than Radios does not. They're zone-based, so we have to do this conversion of our ply-based data to the zone-based cards. Once I've verified that I do have a template property assigned, and I'm happy with the solver attributes here, as well as happy with my fully defined composite data, I can do a laminate realization which will perform this conversion. Can access that by right-clicking the laminate and coming down to Realize. Usually default options are okay here. I will pay a little bit of attention to whether I want to include drape data or not. If I do, typically many more property cards are generated because of the small differences in stack. So to keep things simple, I'll just leave this off. So we should expect our 2 zone-based properties. I will turn delete ply-based entities on, which will just remove our ply-based data. And again, when you're doing these types of conversions, in general, I suggest maintaining your database as a ply-based model in an HM file. And when you need to solve it or get it out of HyperMesh, save this as a new HM, or just don't save it at all. Run your conversion, export the data, and reopen your previous HM with the ply-based model. I'll go ahead and realize here. And upon realization, we see that all our ply-based data is removed, and I have these 2 pcompg properties defined. From there, it's just a simple file export solver deck to write out this zone-based data. This video covers solver-specific requirements and the differences between solvers for composite modeling. It also makes general recommendations on appropriate cards to use when we're building a typical ply-based model. Note, this is not intended to be entirely comprehensive on every single attribute and every single card image related to composites that a given solver profile supports. In general, solver differences boil down to the bolded items on this OptiStruct slide. This PowerPoint has slides for each solver which describe the differences. And using OptiStruct as an example, each profile will have a template property. In the case of ply-based solvers, OptiStruct and Radios, this is a specific unique card. In the case of OptiStruct and Radios, it's a pcomp-p. And note that when you're in these solvers, OptiStruct or Radios, you can directly export a ply-based model. For any other solver, you will need to do a conversion from ply-based to zone-based via a laminate realization at the end of the model build. Every solver has a specific zone-based solver property card, In the case of OptiStruct, that's a pComp-G. And for any solver that is non-ply based, the zone-based property card and the template property will be the same card image. Note, usually for OptiStruct and Radios, this is unnecessary because we can export directly from ply-based to the solver. Every solver has a method of setting offset for shell elements. In the case of OptiStruct, that's Z0 on the pComp-P, and typically this will be found on the given solver property card. It is important to take note and pay attention to differences related to whether the value is absolute or normalized. This varies from solver to solver, and what the typical defaults are for achieving a mid-plane offset, as well as an offset which represents elements at a tooling surface. Material reference orientation and the possible methods vary from solver to solver. In the case of OptiStruct, there are two common ways this is done. Typically, it's a theta rotation from the element system to a given material system on each element, or a local system assignment. If you're using any of the automated tools to generate material orientations, all the settings will be done for you, but it is important as you're using them to be aware of what attributes and cards are being ultimately generated from those tools. In most solvers, the orientation's applied directly on elements. Some, Abacus for example, the orientations are applied directly on properties. And the last common difference where specific solver-based card images are required is for material data. In the case of OptiStruct, typically we're using MAT1s, which are isotropic, MAT9 orts, which are orthotropic linear and can be assigned to both shells and solids, or we're using a user-defined material via MAT-MDS, which allows us to define a multi-scale material. For each solver, like I mentioned, I have a slide describing these differences, and if you don't have access to this PDF for whatever reason, at the end of this video here, I will just briefly scroll through each slide and you can pause it at the appropriate place to view differences for your solver. And with that, that concludes solver-specific differences. And like I mentioned at the beginning, while it's important to be aware of what these differences are, for a typical ply-based model build, the intent is that it's as generic as possible, and 99% of what we covered in the introductory videos applies regardless of the solver you're using.